In this series of videos, we will use Precision Tree to demonstrate the expected value of perfect information. This third video is the final part of the series. The expert with perfect information, the subject of the second video, is a rare commodity. What is more likely is that our expert can offer a forecast of success, but there's going to be uncertainty in that forecast. Let's see how we can account for the lack of perfect information. We'll begin with an influence diagram, and let's compare it to Model 3 and Model 1. The arrow from the success of Sweet Virginia to success means the probabilities of the forecast are conditioned on what the market will really do. The success of Sweet Virginia node is the same as before. Notice the probabilities are unchanged. The success forecast node, presents a table of probabilities that are quite unfamiliar to us. I'll explain them in a moment. Notice the payoff node is the same as it was for the very first model. Look at the expected value table up here in the upper left. The new expected value is $1,399. The expected value with imperfect information is $1,399. The imperfect information is $239 higher than the expected value with uncertainty. Thus, we can actually afford to pay up to $239 for the imperfect information. Notice that as expected, the imperfect information is worth less than the perfect information. Let's look at the expert's forecasts shown here as an event tree and in the table. These are data that we would have to do these calculations. Suppose the expert's track record shows that if demand is strong, he predicts strong 80% of the time. And if demand is strong, he predicts moderate 10% of the time. And if demand is strong, he predicts weak 10% of the time. If the market is moderate, he predicts strong 15% of the time, moderate 70% of the time, and weak 15% of the time. Notice the tree structure. The probabilities of a successful forecast follow the actual market activity. So if the market is actually strong 50% of the time, then he predicts strong 80%, moderate 10%, and weak 10%. So in column C, we find the forecasts. The probabilities of a successful forecast follow the actual market activity, but we will not have the actual market activity, so we need to flip this tree. This is easy to do with Precision Tree. Simply place the cursor on the node name and select the Bayesian revision. Make sure the order that you see here is what you desire. And then you click OK. We want forecast success to be first and actual market activity second, which is the reverse of what it is now. So you see number 2 would be in the top position. Number 1 would be second. I've already done this, so I'm going to cancel and go to the flipped tree. This flip produces the tree we see here, where forecast success precedes the actual market activity. This says the probability of a strong success, given a forecast of strong success, is about 82.5%. So the probability of a strong success, given that a strong success was forecasted, is 82.5%. The probability of a strong success, given that moderate success is forecasted, is about 16%. The revised posterior probabilities are obtained from this table. So the values that we find here are calculated in the event tree that we just looked at. Now let's look at a decision tree to make sense of this Bayesian stuff. We have the same four decision choices: 90 condos, 60 condos, 30 condos, or purchase imperfect information. The upper three branches present the same results we began with for decision making under uncertainty. Let's focus on the purchase of imperfect information. The expert will make a forecast. We will make a decision. Then the market uncertainty will be resolved, and we will finally know what our profit is. So the model is set up that in column C, we have a forecast made. In column D, we make a decision. In column E, the uncertainty is resolved. This subtree begins with the chance of three different forecasts from the expert. The expert can forecast strong success, moderate success, or weak success. The first probability model that we looked at says there is a 50% chance of strong success occurring. And if it does, our experts forecast it correctly 80% of the time. But what we are buying is the expert's forecast, so we want the opposite information. How often is it actually strong when the forecast says it's strong? Here we see a 48.5% chance our expert will forecast strong success. And given the forecast of strong success, the probability that the market will actually yield strong success is 82.47%. So column C shows the probability of the expert's forecast being correct given the value of that forecast. Column C is the probability of the expert's forecast. Column D is where we make the decision. And column E has the probability that the expert's forecast is correct. If the expert forecasts strong success, the expected value of the outcome is $2,328 because we will choose 90 condos under this condition, and $2,328 is the expected value of these possibilities. 82.4% chance of $3,000, 9% chance of $200. Excuse me. A 9% chance of $200. Looks like I'm having a little trouble with that. $200 and an 8% chance of a negative $2,000. Calculate this expected value and it equals this value here. If the expert forecast moderate success, our expected value falls to $587. And the 60 condo choice is best. The expected value of imperfect information is $1,399. This is the probability weighted average. This times this times this plus this times this plus this times this. And that is where the $1,399 comes from. So if this makes your head feel like it's going to explode, that makes you pretty normal. The Bayesian flip is difficult for most people to understand. The value of information calculations are wonderful to have, but they're difficult to obtain. Here is the expected value calculated using the influence diagram. And now that you've seen the decision tree, you understand the nature of that calculation. Note that this example is based on certain payoffs. We are not uncertain about these values, but it is also possible for the consequences to be uncertain as well, and that just makes the calculation all the more tricky.